Greetings, chemists. This lecture is going to be on the topic of calorimetry and phase changes. And we are going to be considering three phases today. So when we say phase, we're thinking solid, liquid, or gas. There are other phases. Plasma is a phase. Bose-Einstein condensates are a phase. We're going to consider these because these are the common ones at everyday temperature, pressure, okay? So we talked last time about the idea that kinetic molecular theory describes how much energy an object has in terms of its motion. So let's look at solids, liquids, and gases, and we're going to think about the molecular level of a solid or a liquid or gas. And I'm going to take water. Okay, so we'll be looking at the same chemical. Chemical will be H2O. Now, water molecules can be liquid, they can be solid, or they can be gas, right? If it's solid, it's ice. If it's gas, it's steam. But it's all the same molecules. They're all H2O molecules. What's going on in each of those cases? Well, a solid, we know if you take a cube of solid particles, they kind of stay in one place. They don't flop all over. They don't change their shape unless they melt, of course. So if you put an ice cube on the desk, it stays in its shape. So a solid, what we tend to assume as chemists is that all of those molecules are in place. They are not able to get out of their spots. They are held there rigidly. They do have some energy. What they do, when they move, if you were to zoom in, let's do a little zoom in there on those molecules, what you would see is these molecules are vibrating back and forth. Okay, they have this little jiggling back and forth, this little vibrational energy. It's not enough to move them out of their spots, but they kind of fidget in their seats, as it were. All right, that's a solid phase of water. And if you were to heat this liquid, put it over a flame or something, they would jiggle faster. You would be transferring in more and more energy, and they would bounce back and forth faster and faster and faster. At some point, that back and forth oscillation would be large enough that they would actually break out of their spots. And at some point, they would be gaining energy. This is like an energy curve. And then at some point, they would start to melt. And you would see little pieces melt off. And this happens at 0 Celsius. Okay? So if you had water down here, let's say at minus 10 Celsius, which is frozen, and you heat it up to minus 9 to minus 8 to minus 7, etc., they would jiggle faster and faster and faster. And right at 0, you would be putting energy in, and they would start to melt out. And once all of those things had melted out, they would now be in liquid form. Now, we know in a liquid form, they don't stay in their shape. Because they're free to move. They can fall down and jumble around. They're in sort of a puddle now. Okay, this is the journey of the particles as they gain heat energy, and now they're moving, and they're moving faster than they were here. They can flow around each other. They're still basically touching each other, right? If you look at a liquid, it's all one cohesive piece, but they have enough movement that they're not stuck in their own spots anymore. Now, you're at 0 Celsius liquid, and you start to heat that up, and it's going to gain temperature, 0, 10, 20, 30, 40, etc. Like we heat it up and keep heating it up with the flame, and they're going to move faster and faster, and you're going to get more energetic liquid until you get to up here about 100 Celsius. And right at 100 Celsius, this graph will taper off, and one of them is going to and start flying. Because once you get to 100 Celsius, they don't actually have to stay connected to each other. They start to leave, and they have enough energy to simply bounce through the air, essentially. And that's when we turn it into a gas, right? Gases have so much energy, they fill their containers. They don't stay on the floor or anything, right? It's like the energy to defy gravity almost. And so we would heat this up, and one of them would jump out, and another one would get enough energy, and over time, all of these guys would gain enough energy to break free of gravity, And then once you get there, they're going to leave that 100 degrees and they're going to start to go 101, 102, and they are now steam particles, and they're really far apart from each other. And, okay, gas particles are not stuck in place, or in place like solids, or to each other like liquids. They are free to fill the container and bounce around and collide with each other, etc. And then you could heat it even further. Okay, so this thing I try to draw here is sort of like a phase graph. So if we had, this was like a graph, and let's say that I have a couple of interesting spots for water. 0 Celsius is one spot, and 100 Celsius is one spot. And this is like energy, right? I'm adding more energy in this direction. The more energy I add, we could take water from below 0 Celsius up to 0 Celsius. And then for a certain amount of energy, we would be stuck there, and that energy is being used to melt the solid, and then we heat it up some more, and it's a liquid now. We're heating it up from 0 to 100, and water boils at 100 Celsius, and right, so the boiling is going to take some energy. It'll take some energy to get those guys from their liquid state into their gas state, and then above 100, once they're all in the gas state, we'll heat them up, and it'll just kind of keep going. So this is like temperature, and this is like energy. Okay, so those are phase changes, and that's what happens. You can go back the other way, too. You took a gas and you put it in a very cold area where energy is being removed from the gas, they would slow down. And if they start to slow down and get so slow, they might eventually not have enough energy to get away from each other, and they would condense. They would turn back into a liquid. And if you continued removing energy from the liquid, they would go down to 0 Celsius, and then eventually they would not have enough energy to even move past each other, and they would get stuck in place, and you could keep going, right? That's the opposite. So if you go this way, this would be from solid to liquid is, of course, melting. From liquid to gas, of course, is boiling. If you go backwards from gas to liquid, that's condensing. And from liquid to solid, of course, is freezing. Under certain conditions, some certain pressure conditions, you can go solid to gas. That would be sublimation. Yeah, sublimation is from solid directly to gas. Carbon dioxide does this at standard pressure. You ever see a block of dry ice, which is carbon dioxide, it'll have like a smoke around it, or it looks like smoke. It's basically vapor. And then if you go straight from gas back to solid, that is deposition. There's actually a method for creating diamonds where you take carbon vapor and you, in a room, and under the right conditions, you can get diamond material to deposit onto a surface. In case you were ever interested. So that's phase changes. Let's introduce this term calorimetry. Calorimetry just means let's count it up. Let's try to get numbers for all of this heat that's going into our stuff. So we'll say we have a block of something, some material, and I'm going to heat it. Okay? Let's make it aluminum. And I heat it up, and it gains some temperature. All right? And we're interested in how much temperature it gains. So let's say you have an aluminum pan. Okay, here's your aluminum pan, and you put it on the fire to heat it up, and it heats up pretty quickly. Okay? It doesn't take much time. Or a copper pan, or any metal pan. Metal pans tend to heat up very quickly. You put them in the fire, and over less than a minute, maybe a minute and a half, they're probably hot enough to cook your food. Now, when you go to take the metal pan off of the fire, you put your hand inside this big, thick glove, right? Or if you take something out of the oven, they get these really thick cotton, wool, or other type of gloves. Those do not heat up very quickly, right? If you grab the metal pan, you know that transfers heat to you very quickly. But if you grab it with the woolen glove, it transfers heat very slowly. All right? So every material out there has a specific rate or amount of heat that it can absorb before it gains some temperature, or rather the rate at which temperature is converted into heat, or heat is converted into temperature. And that rate is called the specific heat capacity. of the material. Aluminum has a very low specific heat capacity, meaning it does not take much heat at all to gain temperature in aluminum. Whereas wool or cotton have very high specific heat capacities. It takes a lot of heat energy, or more heat energy than a metal, for instance, to get these to have a higher temperature. Water is notorious for having a very high specific heat capacity. You have to put a lot of energy into water. Think about boiling water on a stove. You put a pot on the stove and you fill it with water. The pot heats up almost instantaneously, but the water takes forever, right? Because it has a high heat capacity. And the equation that relates these things is as follows. Okay? Q, in this case, is the letter that chemists have used, and physicists, I suppose, to represent energy. And I should clarify heat energy, because there are other versions of energy that have different letters for it. Okay, so heat energy will be based on the mass. M is for mass. The C there is the specific heat capacity, sometimes just called the specific heat, and the delta temperature is the change in temperature. Delta means change, T for temperature. All right, and this is an equation. And so we can use this equation to actually calculate for any given material. If I put this much energy into it and it has this much mass, so let's say this is a 50-gram aluminum pan, that would be a very small pan. Let's suppose it was 50-gram aluminum pan, and I put 3 joules of heat energy into it. If I knew its specific heat, I could actually calculate how much temperature it would gain. All right, and that calculation is the basis for calorimetry. And we're going to do an experiment with this where you guys actually burn a food to try to get the heat out. So, for instance, the food you eat. Most of the food you eat, I mean, it's mostly water, but the structure of the food you eat is largely carbon-based. It's usually a bunch of carbons in a chain. Big, long chain of carbons. More than this, I'm simplifying here, and the hydrogens and other things. And when you burn it, some oxygens come in and react with it, but you have to break those bonds. And bonds that hold molecules together contain a certain amount of energy. And every time you break a bond, you sort of release that energy that it had in there. So if you were, let's say, out for a run, like the fat cells in your body are sort of chained together just like this, you need energy to get yourself moving. Your body breaks apart a certain amount of carbon bonds, burns some fat, and uses that energy to move your legs or move your arms or whatever you do when you're out exercising. Okay? When you want to replace that energy, you eat some food and you break those molecules apart and you reform them as fat molecules in your body so that you have that energy available left, right? You're basically storing those chemical bonds for later so you can use them when you need to. And so people test this, right? They'll take like a Cheeto, and that's kind of what we're going to do. They're going to take a Cheeto and they light it on fire, okay? And they catch that energy in some water. They put a pot of water above the Cheeto, right? And the energy from the bonds in the Cheeto are breaking apart, right? That's what's fueling the fire. And that energy from those chemical bonds goes into the water. And we would say that when it goes in there, we could calculate. We could say, hey, how hot does the water get, right? So we could measure the temperature change of the water. We could look up the specific heat of the water. If we wanted, we could weigh it. We could get the mass of the water. And if we multiply all those things together, that would tell us how much energy went into the water. And if that energy came from this Cheeto, that meant that that was how much energy was in the bonds of this Cheeto. And then we can put it on the back of that Cheeto packet to say this Cheeto had 300 calories or whatever we measured from it. Okay? So that's sort of basic calorimetry there.